So this is the Phosphase Paper Reading Club. We meet up to mostly to be curious and to examine stuff through the lens of science, technology, engineering, and mathematics. And today we examine some real stuff, like the question of finding love. And let me get the papers up. So we have two papers on topic. One is like a classic from the previous century. It aged beautifully. Like the general, like the question the author asks is that, like, it's easy to see that it's hard to find a fulfilling relationship. Like, but as like, you know, as scientists and engineers, we always want to refine questions and get from a qualitative statement, like it's hard, to a quantitative statement, like how hard exactly. And this is exactly what's going on in this paper. And this is like straightforward statistics. Also, like, this is not really useful, so let's do that. This is like really straightforward statistics and statistical modeling, so easy to follow. And what I propose to do here is to like look at the model the author proposes, look at what it look at the implications, and maybe challenge it. Because, like, spoiler alert, one of the persons in the reading club community actually wrote an email to the author and asked them if they did find a girlfriend. So 25 years later, and they did.
Yes.
All right.
How old was the author here?
About our age, I think. Yeah. So like 21 plus minus 3-4 years. Okay. So, like, what the author does here is so he says that often, like, when people get trouble, like have trouble when finding relationships, they come up with like weird explanations, like maybe they are bad at dating, maybe they're too shy, maybe they're too aggressive, whatever. And like these explanations may or may not be useful, but it's always useful to look at base rates, like how likely is an average person, module of those special characteristics you are proposing, are likely to be successful. Then what we do is we, like, there are many people on Earth, like 7 billion or something, and our modeling task here is to refine the set, so kind of like refine the funnel of which people will work for us to build a relationship. So let's start refining the funnel. Like, the author in 99 needs 3 things from a girlfriend. First is she's 21 something, because, like, same age. Second, beautiful. Third, intelligent. Maybe not like mental level intelligent, but like, you know, intelligent. Yes, sure.
So he was 21.
Yeah.
Okay.
So in 99 he was 21. Yeah. Oh, like 21-ish. All right. So we start with the number of people on Earth. I guess it was a little fewer people back then.
Damn. We multiply fast.
Somebody found a girlfriend, I think.
Yeah, so like basically 6 billion people. We halve it because the article is called "Finding a Girlfriend, Not a Soulmate," I guess. Then we only look at people in the developed countries, and it's not because we are like, it's not because we hate people in other countries. It's because if we live in a developed country, then like it's hard. Like the author just, the paper is a joy to read. So I'll quote
It's hard to
sometimes.
reach them.
Like, my chances of meeting a babe from Bhutan or a goddess from Ghana are low. So I have to,
Okay.
yeah, have to only look at like America, Europe, Australia, because that's where I'm likely to live and like ever meet anyone. So yeah, that gave us, we went from 3 billion to 600 million. Nope. Then we filter by age, and I think there is kind of, yes, there are like a few modeling assumptions going on here, because our census data doesn't give us like individual ages, but rather gives us like bins, like 15 to 19 and 20 to 44. So we basically assume a uniform distribution of ages in the bin, and just like slice that interval. And this basically like divides our numbers by 10 again, because I guess many people are either young or old. So this was pretty straightforward so far. Now we get to like maybe more
ambiguous thing.
Yes, stuff which is more up to discussion. So we want beautiful partners, and here the author like again makes a beautiful modeling assumption. Like we don't propose any sort of like general standard. We only say that for every observer, beauty is normally distributed, and so we want 2 sigma. So like, yeah, so we want like top what percent is that? 2 sigma. It's even more. I think it's more. Actually,
66% or something.
yeah, it's actually a lot.
66 is like 1 sigma, 2 sigma is 95, and 3 sigma is 98.
Yeah, so maybe maybe 2.5 is correct actually. No, that's the wrong diagram. Let's use the wrong diagram.
Just Google the sigma table.
Yeah. 6 sigma conversion table. Yeah. What the fuck? No. Yeah. Yeah, so I think this is the right thing. So yeah, it's actually much more than 5% or 2.5%. So it's like 15%.
I like this assumption.
Yeah. All right. Like we just get the CDF and like get the area under the curve and multiply the previous number by the area, and so we get from 66 million 1.5 million.
Again, our preference is to get what top percent of beauty?
Top 15%.
Top 15% from
normal distribution.
Yeah.
Then we do the same. We assume independence between beauty and intelligence, and we do the same thing with intelligence. Only we have lower standards for intelligence, and we only get 1 sigma. So this implies that we discount another 55%, which gets us from 1.5 million to 120,000. Then we get like another crux. And so what we're doing here is we do the same thing. So we do the same filter. So because like beautiful and intelligent, we do not assume like any ground truth. We only assume like subjective observer preferences. And so we can like just do the same thing, but from the perspective of a girlfriend. So like we just divide by those again.
Because the thing is that like the observer has a normal distribution for beauty and intelligence, but then when you look from the point of the thing that you observe, there's a correlation between their normal distribution of the person who's observing. So it shouldn't be like that straight.
Yes, it's like a good point, and it's a great way to challenge this model. Yeah, so like I would expect there to be correlation, and so this number is probably an underestimate.
Yeah.
And so like what the author finishes with is that we started with like 6 billion, we finished with 20,000, And here's what I think is like the weakest link of the auto theory is that, like, say the author lives like in London, and they go on a blind date every night, and so like if they sample potential girlfriends randomly, then they will like never ever meet one of those 20,000. And like I think this is like the main like. I think the way they probably found the girlfriend eventually is they optimize the sampling process, as in they sampled not randomly.
Only take offers with a bachelor's degree. That's already like.
Well, I mean, this does require you to do something like so. I mean, how?
I don't know. Ask.
Just go compromise the Union of Cambridge.
Yeah. So I think that's what they did.
Yeah. So it's not random.
Yeah. So like, my understanding is that the model so far is like generally like solid, except maybe it's like some correlation at this point that also might like me. But this is probably where we can improve on it and like do numeric modeling of like better sampling strategies in random.
The last line is sublime.
This one? Yeah. So, like, any other challenges, thoughts,
I think that could be, if you update this model for the nowadays, I think he should increase number of countries that is possible, because right now the possibility to travel much more wide. Yeah, so it's like a first funnel should be a bit wider.
This model is not like present people like agents.
Yeah.
So
It mostly
the strategies of finding a partner is not discussed in this.
well, like only a trivial one like random sampling is discussed. Yeah.
So it's too general, and now we have more data with with strategies as people amplifies why they're searching for a partner. So if we take them in account, our models may be better.
Yeah, I totally agree. I think this is a great direction for like follow-up research.
So
we need an improvement of the model and like a few algorithms for optimization of the searching process.
Yeah. So like think of like this search space and think of like traversing it and like exploring like different social cliques.
Yeah, that's exactly what I was trying to talk about. I came kind of prepared for this because I have read a book called The Mathematics of Love by Hannah Fry a couple of years ago. It's fun. She's a mathematician from University of UCLA.
Have she had the TED talk?
Yeah. Pretty sure she had it on the same topic. So basically, there are two assumptions here that can be challenged. One is random sampling. It's never random because you have social cliques, and you usually social cliques include people that are both somewhat visually attractive.
Yeah, like social homophily, right?
Yeah, plus roughly the same level of intelligence. So that's kind of increases numbers by default. Yeah, and then the model for the beauty that they have, which assumes the normal distribution, is probably largely incorrect because it's also time dependent. Well, not time itself, but basically people change all the time. People change in really short spans of time. Like let's say today this woman is with makeup, tomorrow it was without makeup.
Do you mean like this introduces noise?
Well, yeah, there is a lot of noise.
One more thing, there's a correlation between preference in intelligence and preference in beauty, most likely.
Yeah. Well, plus the beauty is in the eye of the
Beholder.
viewer,
Yeah.
the beholder, and actually the score of a beauty of a particular woman might change depending on the mood of the viewer, which
Yeah, actually, I wonder if I can look it up quickly, but I'm pretty sure I saw like empiric graphs on how people perceive beauty. Yeah, there was somewhere not exactly that. Oh yeah.
that was it.
Yeah, so what we're seeing here is like red is men rated by women and gray is women rated by men. So men are not very much in luck.
Well, this.
What is data?
This is OCCupid data. It's like used to be a popular dating application in more like 2010s.
So the problem that I have with this, because I've seen it before a few times, is that we only see the distribution of scores, but we do not see the distribution of thresholds that given attach to how likely they are to date someone who is a 3 rather than a 4.
Well, actually, I should have it somewhere here.
Oh.
So on the horizontal axis, ratio between beauty of woman versus beauty of man. Happiness on a date, as reported, does not change. Visit ratio, response rate does change, like a lot.
I mean, this probably should be the same for men.
Great question. I got the impression that it's not like exactly that, but I don't have a graph on hand.
Okay.
But like yes, stuff like that. Also, like attractiveness percentile, messages per week.
Attractiveness of who? Of the receiver of the message or the sender?
Receiver. So like women are likely to get spammed in general, but as they get hotter, they get like spammed exponentially. While like the basic trend is the same with men, but you just like divide it by 10 or so.
How is it 40%?
I'm not sure. Like you have to read the book to find out.
Sure.
The book is actually by the founder of OCCupid. It's full of this kind of graphs. I highly suggest it. Like my only qualm is that it was like published in something like 2015, and like we really need an anniversary edition on Tinder in 2025 something.
We need a school subject on finding love. A school subject on finding love is what the world needs.
Instead of gender studies.
Not the study why I will never have a girlfriend, but how to get a girlfriend.
Yeah. So I think we basically covered this one, and it's a good time to go to the next one on the same subject, and those were like pretty short and sweet.
Is it a real paper?
I mean, like this one, I'm not sure where it was published, but this one,
this one.
It has worse formatting, so I understand your question, but it was presented at the Warwick Economic Summit in 2011 or something.
It's not even in what?
Well,
it's not science.
economists,
Okay.
Lazy guys.
Yeah. So like, it's basically the same thing, but using a different like statistical model.
Using all simulations existing in the galaxy.
Yeah. So like, the Drake equation is basically a Fermi decomposition of the likelihood of finding intelligent life. So like it's hard to estimate the likelihood of finding intelligent life directly. So we like decompose it into a number of variables which are like easier to estimate. And here are those variables. So like this is our target number, a number of civilizations. And here is like our variables we decompose into. Rate of formation of stars. This is like a physical question. Average number of planets, similar to Earth, again, like astronomy question, empirical one. Fraction of Earth-like planets, fraction of Earth-like planets where life develops, fraction of planets where life developed which can communicate, like have radio or something. And then the length of time a civilization will survive, which is like useful because like it means that like at every point where civilization lives, we get a chance to hear the signal. And like to make it more concrete, how do these numbers look like actually? This is how they look like actually, at least in Drake's original work. So like 1 star formed per year, fifth to half of all stars formed planets, 1 to 5 planets developing life, all of those planets will develop life, all of those planets will develop intelligent life. Very generous assumptions, like outrageously generous assumptions.
1 to 5 stars have planets that develop life?
When a star has a planet, it will have between 1 and 5 planets capable of developing life. Again, like very generous, super generous. 10% will also be able to communicate, and they will survive between 1,000 and a very large number of years. So super ultra generous assumptions. And if you plug those very generous assumptions, then you get n of 20. So like 20 civilizations must be out of there. Which, like, I'm not an expert in Drake equations, but this to me suggests that if you like if you decrease one of those numbers to something maybe a little more likely, then your n goes to shit quickly. Which gets us to the question of finding a girlfriend.
That would be less hype.
So it's overfitting.
Overestimating. Oh, at least like so. I think Drake's like contribution was mostly to propose this sort of decomposition, and like follow-up researchers came up with better numeric numbers to plug in. But also, the Drake equation has like a flip side. So even if we're very generous and say that there are like 20 civilizations somewhere out there, if we again like, resort to random sampling, so if you like pick a random star, then we are shit out of luck. Like very unlikely it supports life because like the universe is vast. Okay, and yeah. So like the way people used to think about it like I say, at least used to think about it in the 20th century is that like there is a chance that alien civilizations are out there. This is not like some wide science fiction. It seems like reasonable and like reasonable assumptions. And this is exactly how a question of finding a girlfriend looks like. So like there is a chance. It isn't science fiction.
Not a science fiction.
And here's how.
Yeah, and some guys already saw them.
Yeah.
They exist.
And like there is a bunch of movies with girlfriends.
Yeah, so.
Okay, so here's how we refine the equation to work for girlfriends instead of aliens. Our target number is the number of potential girlfriends. The author is mostly a heterosexual male, so we focus on girlfriends.
I really like his that he said it mostly.
Mostly.
Yeah, mostly.
Then like we take the rate at which the population grows. This corresponds to the number at which stars form in our previous equation. We take the fraction of people who are women who live in London, women in London who are of the right age. Again, amazing language here. Like, I don't want to fall prey to a voracious cougar. Yeah, so no Al Pugachev for this one. Women in London who are age appropriate and have a degree.
Which one degree means?
I assume it is bachelor's.
Yeah. That's what he means. And those the author will find physically attractive. Here, like he doesn't even try to do distributions or something. He just said, let's be generous and say I like 5% of women.
Damn. It will be great if you could compose two of those papers with the distributions for the it's a bit more like scientific.
Yeah, and also like
not much.
This is underestimating, I think.
Yeah, I agree. Let's mark this in red or something.
Alert.
Yeah, but on the other hand, he's overestimating in the last parameter. So in the parameter of like the time span that he had to find a girlfriend so far, he says it's 31, but it's probably not 31. It's probably like half of that, right? Because he probably wasn't looking for a girlfriend when he was a toddler, unless he was a very beautiful toddler. Okay. There is like a technical tidbit where he replaces population growth by just taking the population as of a certain year. I think it's not very interesting. And so like we get this refined equation and we plug the numbers and we get 10,000 people who are girlfriend material in London.
He, by the way, didn't add a component for the women that may find him attractive.
And he also didn't get a component for intelligence.
He had a bachelor degree.
Also, they could be married, actually.
Yeah. So like probably an overestimate, sure. He says that like this looks like a small number, but if you like if you multiply it by 1,000, then you get that it's actually a 1 in 1,000 chance. So maybe you only need 1,000 date nights. No, actually, he does say that this does not take into account the fraction of women which you find attractive depressingly low, and the fraction of women who will be single. So like our generous overestimate here is like 1 in 1,000 baseline. Then we apply the same correction for women who are attractive, who are single, and like who will match. So we just like divide by 20, divide by I'm not sure where his number for single is, but yeah, I think like he basically divides by 20 and then divides by if there is a 10. So we divide 10,000 by 200, and we get 26. And we get 26 women in all of London with whom you can get a beautiful relationship. About 100 times better than finding an alien civilization by Drake's estimates.
You know, if we take into account the rule of 6 handshake, it's real fun. So.
Mm-hmm.
You handshake a lot.
Yeah. So like I do agree that I think like the main next frontier for this field of scientific inquiry would be to work on like strategies and like viewing people as agents and working like considering social cliques.
I started with some of that.
Yeah, more of that. There is nothing about wonderful relationships. It's all about like match. Yeah. Oh, he's attractive. She's attractive. Let's chat. That's it. There's no work about actual relationship.
You know, life after that does not exist.
Yeah. It's the end of the film.
Yes, it's just that.
Happy and what?
Yeah, happy ending.
It's fog of war after that. Fog of war.
Fog of war.
Yeah.
Mm-hmm. Yeah, also great point. It would be interesting to have like an end-to-end simulation of like incorporating both like the chances of divorce or like strife in a relationship, and like like maybe an interactive map where you can like pick where you live, state your age, and then like get I don't know a number of years of happy relationships you're likely to have.
Given the first assumption that he gave, that he's mostly heterosexual, I'd like to propose one thing. Is if we include his Kinsey score, for example, as one of the parameters, do include the male population there too, include homosexuals, which do have a much lower rate of stable monogamous pairs. He has a much greater chance of finding a male partner rather than female.
We could also include transgenders.
Oh yeah.
Yeah, it sounds great. Like input your Kinsey score as a float, like with many digits, and like see the likely like the mass of your dating chances which come from different genders.
Yeah. Very fun.
All right.
So this paper saw the previous. It's not about actual having a good relationships, but just about have a match with or have a first date with somebody, right?
Well, like the author kind of very lazily gestures at the question of like getting along, and he. Oh yeah, I actually misspoke earlier. So like he divides by 20, then by half, and then by 10. So a larger factor than I said.
Oh.
But yeah, like I don't know if it's a good estimate or not. So like 1 out of 10 people you have like a chance to build a lasting relationship with. Don't know. Okay.
It depends again on the strategy of data, I suppose, because if it's only from the cross connections, then this figure might be alright. But if it's from Tinder or something like that, it's much lower than that.
Yeah, definitely agree. Like one thing I'm very confused about is why there is like seemingly so little data-driven public research into dating.
Actually, okay, I have a friend who
Is hot?
I know. My friend who is
Complain.
who complained to me that he has like 0 matches in Tinder. So he's like, oh my god, why? So and I found a video where a guy made a numeric simulation of dating with some assumptions, which present why average guy have 0 average matches. So this is more like on the earth because it
Because
shows
it's
that
like
we
an
have
empirical
strategy to
probability,
go to Tinder and something like that.
Great point. Like my general intuition is that like so same as when you're looking for a job, it's LinkedIn published the results that like 80-90% of like open positions are filled with networking and not with like code applications.
How much?
Like 80 to 90%. This was not a very rigorous study, and they don't have open data and stuff. But like it's the numbers they put out, and I suspect kind of the same to happen in dating. So that's why like cliques and like university prom nights are likely to be very effective.
Also, the fact that the business model of Tinder is to have you continue swiping leads us to 2 things: no open data and quite low effectiveness of the method itself.
Yeah, it would be much more, like aligned with users' interests to have a dating app for swingers because it's like about you have a long-term relationship and you find new people and like it's a lifestyle thing.
Yeah, they need to earn money.
Yeah.
I think the problem of having the more research in this area related to the data privacy, partially because companies don't, for maybe different reasons, don't want to share about their data. I mean, data implications, how they actually look like in terms of statistics. Yes, and that's why maybe it's kind of a blocker to have more studies in this area. And to aggregate, if you want to just, I don't know, aggregate real data and simulate it, you need to spend a lot of money, and I don't see a lot of applications after that. So who could invest in this? Lots of questions without answer for me.
Mm-hmm. Yeah, well, I can see that, and like it is conceivable to me that we have those like fun plots from OkCupid, mostly because like the founder of OkCupid was like a social scientist and he like wanted to have fun, but like most people don't want to have fun; they don't want to get sued.
It's similar to like famous bloggers. So 1% of most famous bloggers, they have like 99% of popularity.
Mm-hmm. Yeah, it's similar, sure. All right, so I think we are basically done with these two papers. I propose taking a break and mentally preparing for the hard parts.
Now, the next part is why we don't have bureaucracy.
Could you, I don't know if the guys already been on the previous events, could you introduce us to this series of events?
Yeah, sure.
If you are a maintainer, right?
Mm-hmm. I guess I am. So
maybe previous was hosted by another.
Mm-hmm. Yeah. So like let me get a picture up or something. So this is the Four Space Paper Reading Club. It happens like every 1, 2, 3, 4 weeks on average. And it,
how long?
I think we've been going at it for a pretty long time now.
Okay.
Maybe, I know.
For a year.
Yeah. Though with some gaps. Like sometimes we have like weekly seminars, sometimes we have like monthly seminars. Depends on if you have fun stuff to share. And this is like. So I think there are two things to say here. I think my vision here, like my personal vision, is to examine fun ideas and be open to weird ideas. Like my current interests are in like statistical modeling and AI foundations, I guess. But I also used to do programming language theory, so that's why the second paper of the day is a connection, like it's a link between AI and programming languages or like computational models, computability. And like the way this all works is that like someone, maybe me, maybe Mitya, maybe someone else proposes papers and gets them into our chat. This is our chat, and is like, hey, here are some papers. I want to check them out, and everyone is like, yeah, sure, check them out. They're so fun. They're so exciting. And then we just schedule a date and meet up and discuss them.
Our topics are like.
Topics aren't really fixed, so
Not fixed, okay.
yeah. So like Mitya's interest in
It's not like
is in
ML paper.
not really. So like Mitya's interest in 3D stuff. So he
So once every month I do a lecture on computer graphics, 3D related stuff.
CV.
Computer vision, yeah.
yeah, like I'm interested in modeling and AI foundations, so I talk about that. Sasha is interested in programming language stuff, so he talks about that, and like it's really like really open. The general format is just like have a paper, post it so that people can read it, then meet up to discuss it.
Yeah, but now for the second time, there's no link to a paper.
I forgot.
But there is a paper.
Yeah, there are two actually. 3 if you depend on how you count, or actually more. Yeah. Okay, that's like
The whole stack that follows.
I mean, yeah.
So how many main contributors, main hosts to this?
I say like I think there are 2 people who do stuff like really regularly. This would be me and Mitya. Yeah, and there are 2 people who do stuff like sometimes.
And you sometimes choose topics about LLMs. Right?
Yeah. Yeah, that's my current research interest. Like, that's my current. I currently work on LLM safety, so yeah.
Do you have sometimes topics about crypto?
So like.
Because my friend is really interested.
Yeah, so like there are a bunch of people in the Hackspace chat which are interested in crypto,
Okay.
but so far they have mostly been like, oh, we're so interested in crypto, let's do something, and they're
Let's
like
make money.
crickets, like nothing.
Alex, you should do a presentation
Yeah, sure.
about what you do to me, to explain me, because I don't know even now.
And about the moon, I often wonder about the stars and about the clouds.
So let's go with the harder part of today's agenda. It's I don't know, like it's a pretty complicated subject. So like let's try to think about it step by step. So like we have a transformer, a deep learning model. Deep learning models are famous for being like black box and interactable. So like you give it a picture, it tells you if the picture is of a cat or of a dog. Of a cat or of a dog, but like you mostly have no idea how it works. And people are interested in knowing how things work for a bunch of reasons, because knowing how a thing works, you can fix it efficiently, you can optimize it efficiently, you know like the boundaries where it is likely to break. So like a lot of good reasons to understand how things work. And today's paper is about approaching this from a very particular angle. There are a lot of angles to this. This is just one particular one. And like, so I think it's useful to contrast these like transformers are a particular deep learning architecture, recursive neural networks are another particular deep learning architecture, and recursive neural networks have an advantage. Let me look it up. Yeah, the advantage is that LSTMs itself, so like RNNs and LSTMs predate transformers by like 20 years. Transformers are like 2017, LSTMs and RNNs are like 97. This means that a lot of theorists had the chance to do stuff. And what this gives us is that for like prior architectures, like say for RNNs, we have a formal model of computation. What I mean to say is that like you can model an RNN as an automata. So like you have an initial state, you have like transitions, probability of transition, like, and why this is useful, because when
for learning or for inference or for both?
I meant inference. Yeah, I meant inference. I'm not sure about learning. So like, I mean to say that when we have like a concrete RNN, we can model it. So like, we can represent it as an automata.
As an electronic scheme.
It means mostly as a whiteboard drawing. So like, you
State
know,
1, state 2 probability of
yeah. So
State
like,
machine.
yeah, state machine. State machine is a good word. So it's like state 1, probability that to transition to state 2, probability 1 minus that to remain here. So like this sort of thing.
What?
A bit more complex Markov chain.
So it's mathematical model where
Yeah.
we have like some number of
Окей.
Короче, у тебя RNN, она проходит по последовательности там входных векторов, и каждый раз, когда у нее прописного вектора, она переходит в новое состояние, в кавычках, и это состояние можно выразить так математически, как типа граф, что она скакает по вершинкам этого графа.
Okay, before you continue, before you continue, could I ask you a question? So it's more about the interpretability, or it's a bit other angle?
Can I like postpone this question for like a few minutes?
Okay.
Of course. Sure.
Yeah. All right. Okay. So I think it's not like, if you're not familiar with automata, it's not very important what automata are.
Okay.
It's just important that we have like So like,
what is the profits of?
yeah. That's what I'm going to say. Like, you have a platonic ideal of an RNN. You can instantiate it in a few ways. You can instantiate it as matrices you multiply. You can instantiate it as like a Python file you launch, and you can instantiate it as a whiteboard drawing. And why? And like, some sorts of whiteboard drawings are better than others, and that is because for some you have like a rich formalism, which like the formalism we care about today is called, I guess, theory of computability of not Siri. No, Siri, go away. Yeah. So like computability or like algorithmic complexity theory, this sort of stuff. And like you might recall stuff like the P complexity class, the NP complexity class, so this sort of thing, or like Turing machines, or like restricted Turing machines, or like random access machines, or like all sorts of machines. Yeah, like this automata are basically a bridge to this world. So like machines, complexity classes, and like, if you like, on first glance, it's very unusual to connect the world of like deep learning with this other world, but like there is a way to draw utility here, and it's what we're going to do when going through the paper.
Okay, it's kind of bridge between classical computer science approaches, and
yeah. So it's a way to leverage like the power of traditional computer science in this domain.
Yeah.
Yeah, I think this is actually I mentioned like that. Like about the papers we have for this, we have the two main papers: thinking like transformers and compile transformers as a laboratory for interpretability. But I'd like to start a little earlier on. So like, these papers are 21, 23, and this paper is like 20, and maybe we'll refer to something from 18 or so, because it's like just an easy introduction to this like particular research subfield. Yeah, so let's try to see. the way this this subfield works is we have like in theory of computation, or maybe in computer linguistics, or like in this fields of classical computer science, we have formal languages. We have like Boolean expressions of rank n. We have Dick languages. We'll get to know what a Dick language is. Yes, I'm really saying these words. Yeah, so like Boolean of n, Dick of k, and like the way you can think about that is that so imagine you have like a particular language which consists of braces, as in like this sorts of braces, or maybe this sorts of braces, and your task is to say if a particular expression is balanced or not. Well, like we can do different variations of the task. So like you can say like this expression is balanced because like we don't care about order. We only care that every brace is eventually closed, and like this expression is not balanced. And the question in terms of like computation theory is how complex a computer, or like how complex an algorithm in terms of time and space there exists to solve this. And like to briefly like showcase, the idea is that we can evaluate like standard algorithms on this sort of thing, and then we can encode these algorithms into transformers. And if a transformer successfully encodes a given algorithm, it says that it's at least this expressive. If it cannot encode a particular algorithm, it means it is not that expressive, which is to say like that this particular transformer architecture with this number of layers, this number of heads, this kind of attention is not X expressive.
It's very similar to like B and B problem modeling.
Yeah, exactly. It's just like encoding into deep learning models. And like to give you some more intuition, so some, like maybe early deep learning models had intuitively kind of mapped to classical computer science concepts, because like if you take an LSTM, long short-term memory cell, then it has recurrence and it has state, which is a lot like a machine, and which is useful because like it gives an intuition about what it can represent. But a transformer does not have recurrence and it does not have state, so it cannot like directly count. But empirically, we see that it can kind of count, especially if we give it like a trillion parameters.
What does it mean to have recurrence and state?
I mean to say that so in an LSTM, we have
And state?
Yeah.
And you mean like in a transformer we don't?
Yeah.
But it can definitely model it through like one of the tokens. Like just imagine that this will be our hidden state.
Yeah. I mean, yeah. The question is about scaling this kind of thinking.
I think there are even papers that add a new token for it.
Okay. A few like other points of intuition from this paper, and then we'll go to another one. In this paper from 2020, the authors show that for like particular languages, which are like basically of the sort I showed you, like basically balanced in parentheses, if you learn a transformer to balance parentheses, it will use self-attention to maintain a counter, which is in itself kind of interesting because it is about how how algorithms, how computations are learned without like explicit direction. So
by balancing races, you mean like it is given a sequence of races and then you should predict the next race and so on until it balances?
Actually, great question. I didn't read this paper beyond those 2 pages, so I'm not sure what their particular setup was.
I think the balance, the braces, is meant just estimate if this particular sequence of braces is balanced or not.
Yeah, that's what to expect. So just classify if a given sequence is balanced or not. Also, like just as a side point, consider just how easy it is to perform experiments in this agenda, because like you don't have to like collect real data. You just like you have a formal model. It can synthesize your infinite data and infinite right answers. So it's like very easy to try to find a simulation, or like a deep learning simulation of a classic thing. Yeah, and like what they go on is they like continue trying different variants of those languages. So like different like you might also recall from your like university course the thing about like grammars. The grammars can be like they might require like state to parse, or they may be like they might be free of that. Yeah, so like they consider different variations of languages which like require harder and less harder parsers in the standard sense, and they draw some from this what different components. So like a transformer model is a transformer architecture is like somewhat ad hoc, as in like it's a bunch of things and it's not like immediately clear like from first principles why these things are there, right?
True. It's clear to me, but okay.
I think like my thinking is that it's clear like post hoc mostly, as in like we glue them together and like we run a shit ton of experiments and then we say, okay, like this component seems to do this thing. I'm just not sure that it was like known beforehand.
Yeah, it seems like that you have lots of research to adding like this multi-head attention and so on. So first of all, you like explore attention, how it works, and the multi-head attention and so on. So from the first glance, it doesn't seem like very logical how it looks like.
Yeah, that's how I understand it. And like so, this paper, this is one of those papers which studies different components, and it tells us how the different different components of the design contribute to the like ability to model a given complexity class, to work with a given complexity class. And another thing, another 2 points to highlight from this paper, and then we'll go to another one. Point 1. So this subfield is different from other interpretability or DL foundations approaches, because so like classical interpretability is what the authors here call like finding what information is contained in intermediate languages, but I like to call it by a different name, which is Bertology. And this is an actual word you can like you can look up.
Is it still a thing?
It's well, I mean,
I'm sure it'll be like 3 or 4 years.
It was a thing in 2020, right?
Right.
So like, what was Bertology about? Bertology was about we have the transformer architecture, and we have 2 major language transformers, which are GPT and BERT. And BERT is like more interpretable for reasons, and we can look at its attention map, we can look at its attention map and like feed it some model sentences, and just from the attention try to figure out what's going on, like what this particular attention block represents. Or we can train like our own transformer on a simple task, like a task of like playing some game, like some simple version of chess, or like some simple game, and again, like we can look at attention map and try to figure out what's going on, and there are some cool results about attention, or like a prior way representing like exactly the 2D map of the game, for instance. So this was Bertology, like looking at transformers attention to understand what it does. And the paper we are slowly easing in towards is not about that, but like it's just another approach and just like highlighting the breadth here.
By the way, it's like common in computer vision, like the dyno model that is very widely used right now in computer vision as like a feature extractor. There's also like lots of papers that use that model, look at its attention map, and see that like its attention map highlights different objects. Stuff like that.
Yeah, and like let me take a little bit of like I don't know. Let me stand on a high horse here and say that like to me this sort of research feels kind of you know a little bit beneath the dignity of humans, because beneath the dignity of humans, this kind of research, because like you literally have like people looking at attention maps all day and trying to figure out what's going on. And like, I mean, yes, but maybe you could automate that. And the paper we're easing into it is exactly about automating that.
The idea that I was talking about is that like they have attention maps in different layers, and like this particular attention map very well highlights the separation between objects. And also the experiments show that this particular attention map is best for like inserting somewhere into another model, and so like this visual intuitive is supported by experiments.
Yeah. Okay, so that was Bertology. Another thing here, like apparently in 2019, someone showed that transformers are Turing complete, and I wanted to like talk about this result a bit. So there is a well-known result in deep learning that like multi-layer perceptrons can approximate any function. This is called the universal approximation theorems, and it's theorems because much like in completeness theorems, it's more like a lens which can apply to a particular model and get something. I have write it as UAT, universal approximation theorems. And like, I think this kind of begs the question: what are we even talking about if, like, I don't know, like from year 1980 or something, we know that we know that multi-layer perceptrons are are universal approximators. And like, what does it mean to know that transformers are Turing complete if transformers have multi-layer perceptrons and like.
By the way, to be fair, I don't think transformers classify is multi-layer perceptrons. Their layers have different operations rather than. I don't think you can model any multi-layer perceptron as a transformer layer.
Yeah, I agree. I was referring to like the fact that we normally like slap another MOP on at the end of the transformer.
Sure.
And like, is it the case that transformers like are dumb, but the final perceptron makes them like super smart? Like maybe they're just encoders, right? And maybe the perceptron does a useful thing. Okay, like the difference between Turing, actually it's like three things I'd like to build towards here. So first we have this universal approximation thing, and normally, so like you can look it up to get a precise statement. I'm going to show it to you, but I'm not going to really talk about it. This is like the standard form of the universal approximation theorems. There are many, but it's like the people normally refer to. And yeah, I guess like only one thing I like to highlight from this like screen of mass, it's this like compact K of Rn. And what this gives us is that it can model an arbitrary function, but this function is basically in Rn. So it's like
Finite dimensional.
well, like for every n, Rn, but yeah, well, like this is also compactness, but like a real function basically, okay? And statements about Turing completeness are something different. They are more about like the internals, so they are more about like I'd say they are kind of like we can simulate this. They are kind of we can simulate this kind of automata. So like this is stated in terms of like we can learn a real function, and this is stated in terms of like we can have this sort of rich internal world. So like Turing completeness is like about how computation happens and not is the result of computation. Because like why am I highlighting it? Because like you can get a trivial like universal approximation result if you say I have infinite memory and I can remember every input and output. Mm-hmm. So it's useful to say that like we have some internal structure which can compress that a lot. And this was like step one. Okay, actually let's say this was step one, this was step two. And step three here is to say class X, which is like P and P or a particular class, because Turing completeness is also a qualitative statement, as in it says like given infinite space and time, this can model particular automata. Oh, well, maybe not infinite space, because like infinite space would give us like just memorization of everything, but like it's a qualitative statement.
Oh yeah, Turing machine. Well, the general definition of Turing machine is infinite. So
infinite, but the program should finish in finite time.
Yeah.
Yeah.
So this is Turing computability, which should hold.
Mm-hmm. So like Turing completeness is kind of stricter than universal approximation, and when we say that an algorithm has a particular space complexity class and a particular time complexity class, it is stricter still. So for transformers we have Turing completeness, we have universal approximation, and what we are building towards in today's seminar is complexity classes. And I think that's it for this paper. This was on the ability and limitations of transformers to recognize formal languages. Okay. Let me see if we want this one. Yeah, let's also like look at maybe page 1 and 2 of this one as well. Again, we have classical results that LSTMs are a variant of some machine or the other, like which can count to k, I suppose. And they can recognize dic n, where dic n is we have n different types of brackets, and the expression is nested correctly. And apparently Chomsky invented it. Well, like Chomsky in 1959.
GPT can't do this, said Chomsky.
Yeah. Yeah, so like a formal language where you balance strings, and we have results that LSTMs can balance strings with one type of brackets. However, we have like this is going to be weird. We have a hard result that LSTMs cannot do dic n larger than 1. And this is like very interesting because like you like I think deep learning practitioners like never have this sort of results normally, or at least talk about them.
Yeah, the task is for STM to classify whether it's balanced or not.
I'm pretty sure.
Assuming.
Yeah. And there is like another paper which shows that transformers will also fail D2. So because they will work for D1, I suppose, but will fail D2. If you give it like as like it may work for a string of length 100, but if you give it a string large enough, like this is not a general algorithm in length of string. Also, I expect that like this paper has some particular assumptions on a transformer. So like some particular kind of attention, particular kind of heads, whatever. And what this paper does, I think they basically do two things. So on one hand, they do Bertology. So this is an attention map, and the way you read it is violet is low activation, yellow is high activation, and if you really like squint, then you can see that. What can you see? You can see that a thing activates to itself. So like left bracket to left bracket. You can see that left brace to right brace, or left brace kind of stands alone for whatever reason. Yeah, so like I didn't actually squint at this diagram for a long time, so I'm not going to do it now. I'm just saying that like this is the kind of thing that people actually do for a living. So yeah, like look at this sort of diagram and try to figure out like the causal relation.
No, not.
You want to spell it out? Okay. Yeah, so like activation map for that was D2. We also have one for D4. I guess what we can see here is that like this thing looks the same, but the other thing looks different for whatever reason. Like I'm not going to do Bertology today. Oh, actually, but we do have the autos interpretation, so let's try to figure it out. So what the autos say is that so like we have this old result that transformers can do D2, but if we add like a start token, so a special token which represents start of sequence, then it works for DM somewhat. And the way it seems to work, if we squint closely at this picture, is that we learn like a stack machine. Yeah. So like if we see close bracket, then we pop open bracket, and then look at brace, and then we have leftover. Yeah. So like this is some weird shit because like we just learned the stack machine.
By the way, why does LSTM not learn a stack machine with like a sufficient kind of state?
I can't really answer that well. Besides that, so I assume that. Well, I mean, like my computability class was some time ago, so I can't quite recall like what a key counter machine, push down automata, and like stack automata are, and how exactly they differ. But I suspect that if you like just look at the definitions, there will be like a concrete detail. So like apparently LSTMs are not push down automata. Maybe you can augment them in the same way we just augmented transformers to give them that capability. Yeah.
Pretty sure you can augment it by using multiple LSTM layers, but not stacked, rather than parallel. So yeah, the classification.
Mm-hmm. Yeah. So I like to think about this agenda in terms of like saying that like this block, like say LSTM block, gives us like this much computational power, and we have those composition rules that say that like if you like parallel them, then you get like this much power. If you concatenate them, you have that much power. All right, I think that's it for what I wanted from this paper. This was how conservation networks recognize decam languages from 2020 as well. Surprisingly, that was Visa research, like whatever. Okay. Yeah. All right. So now we get to what we actually wanted to study, which is what. So let's just look at the introduction. What the authors do is that they stare at the transformer architecture long enough that they come up with data and control flow primitives, as in like programming language primitives, like for which correspond to the transformer architecture. And like if they come up with those primitives, then it's a short way from there to a programming language. And what this gives us is that so like Bertology is you have a transformer and you try to reverse engineer it to find what program it encodes. But if you have a program which you can compile to a transformer, you can do the opposite thing, and like you write a program, try to compile it. It either works or doesn't. If it works, then like the transformer is this expressive. If it doesn't, and this is RASP, the restricted access sequence processing language. And another like nice thingy we have. This is like just a shout out to the authors for like doing great analysis. A RASP program gives us an estimate from the top for the max number of heads and layers in the target transformer. Okay. And like another piece of prior work for today, and then no papers from 2020. So like there are some like early results that transformers can do reasoning, as in like, and let me just show you what we mean by reasoning. We mean, you know, like this basic inference stuff, like Aristotle sort of stuff. We have facts and rules, like we have Alan is blue, Alan is rough, and we have all rough people are green, and like Alan is young, but Bob is round, and if someone is young and round, they're kind. And so like it is like, you know, this sort of thing which they teach you in school to solve with a Boolean table. And the answer, like, and the question is, can the transformer
Be about.
Yeah, exactly. And the answer is yes. At least for first order statements. And these are like all first order, we have no quantifiers here. Oh, actually, we do have a quantifier here, but we don't have like, it's a first order quantifier. So like we don't have any statements about formulas here. Yeah, I think this is about all I wanted from this paper, except to say that like in the literature you might see like theorem prover, or like logical inference engine, or like hard reasoner, and this is like classical reasoners like Prolog, and transform like deep learning models sometimes called soft reasoners because like the inference is not like Boolean but probabilistic. Okay. Yeah, and so like we when we are working on a programming language for this sort of thing, what we want to get is like we have this very nice property that when you write a RASP program, then like you have you get a transformer representation of a task, which is interesting because like much as Bertology research is about like looking at attention maps really closely, so this is like reverse engineering transformer. If you don't have RASP, when you want to craft a transformer which does something, you mostly craft it by hand. That's just not fun. Or like you can learn it on a model task, but if a model task isn't simple, then like you're going to have like learning junk. And so like I think like what most researchers do is they like try to learn something, they look at attention, then say like, okay, this is probably the useful part, this is probably junk, and they like try to relearn, like patch some activations out and see if it still works, and like so like a bunch of manual work of this kind. And RASP is one of the tools which lessens this workload. There are others as well. Also, I think that like we kind of went through a bunch of stuff now, and I propose taking like a 3-5 minute break.
Okay.
About the star and about the cloud and about the moon, I often wonder.
All right.
Beep beep.
We begin with an informal overview of RASP with examples. All right. So that like this is going to be somewhat hard, and I'm not sure like how much progress we'll make, but let's do our best. So like point 1, transformers computations are applied in parallel using attention to focus and on tokens and combine them. This is unlike like standard computational model of standard programming languages. And because we are doing the computation in parallel over the entire input, our like iterations go not over the length of the sequence, so it's not 4 over the length of the sequence, it's along the depth of computation. So it's not like over data, but rather over computation. Yeah, so like the number of layers that I apply to input as we work towards the result. So this is, I guess, quite, it's quite like standard 4. I wonder if it's alike to like RNNs.
I mean, it's particular to RNNs where like RNNs have all layers, but 4 over. So the sequence here, it's 4 over the layers, but the sequence is in parallel.
Yeah. All right. The computation model. The input is 2 sequences, tokens and indices. Indices are like they're constant. Like they're just like this is basically like positional encoding, I guess. So like the user provides tokens, and our RASP program, what it gets, it first like gets the string with tokens, and it also gets an index for each token. And the output is a sequence. This was like input is tokens and indices, output is like sequence. You can make a sequence from a sequence by applying element-wise operations which are broadcasted. So like if you do 1, 2, 3 plus 4, 5, 6, then you get point-wise addition. If you add a constant, you get broadcasting. If you like take the power, you get broadcasting. If you do a binary comparison, you get broadcasting because only 3 is larger than 2. So like this is element-wise operations. It's simple. A harder thing is like weird shaped operations. We have select, where select, I wonder if we have a nice, no, we don't have a nice, so let's go with what we have. Like, okay, we have select. Select takes sequence K, sequence Q, and the predicate, and returns a matrix such that every matrix element takes like K to Ki's and Qj's, and thus it's binary thing. So to take a look at that, we have a sequence 1 to 2, we have a sequence 0, 1, 2, we apply the binary comparison, and what we get is that 1 is equal to 1, and 2 is equal to 2, and 2 is equal to 2. So like, this is just like maybe somewhat unusual because vectors and matrices, but this is like just compare, so like go through a column vector and a row vector while applying a user-specified operation at every pair. This is select, and then we have aggregate, which takes a matrix and the sequence, and returns a sequence such that this is kind of weird.
It's literally just matrix multiplication, right?
It's exactly right. Yeah. So this was S. This is the S we got from the previous step, and we have 4, 6, 8. And what happens here is that on row 1 we like no mask, like all masks are false, so we get 0. On row 1, 1 mask matches, so we get 4. And on row 3, we get 2 matches, and so we take the average. So these are like somewhat weird primitives, but like all right, they like we can understand them. And like aggregate is the only way to combine values from different positions. That is to say, you can get like if you have sequences, you have 2 sequences of length n, you can do element-wise to combine tokens at same indices, but to combine tokens at different indices, you can only use aggregate. Okay.
Did I understand correctly that like this second part, the select aggregate, is literally just attention? The first part is we use the universal approximators, like the MLPs that we have in the.
That's right. Yeah, that's right. Yeah, like they give us this example that you can do the following in Python, where you have a list A, and you take constant first element of the list, and like you get a new list of length A, which is all constants first element of this list. And the way you try this in RASP, you would say select indices 0 equals to select the first element, and then aggregate with this selection matrix over A, because like this is just how these 2 operations will compose. A small technical detail, this is not really important, but they bold it, so let's mention it. So an implementation detail of this language is that it is lazily functional. That is, if you have, I think, if you have S1, which is a function, and you have S2, which is a function, you can say function plus function, and you get another function. And when you call S3 of x, what will compute is S1 of x plus S2 of x. So this is not really important, just design. Okay, so what do we have next? Next we have 2 program examples. we might want to take other examples because these are somewhat require some theory net. Yeah, let me try to get us other examples. I think examples here are a little complex as. Oh well, actually this one might be alright. Oh no, it refers to. Well, let's try this out. So like this is a sorting routine, which I think it takes a list of numbers and returns a sorted set of numbers. So what we first do is we select over the very same sequence with less than or equals, and with that we get like a triangle matrix. Yeah, I think that's right. And then this is like a routine which is in the standard library, which is implemented in pure RASP. We get I think this is the rightmost true in the matrix. So like for each, this gives us from the it gets us from a matrix with token comparisons. It gives us the position of the rightmost less than or equals. So it gives us the target position of an element. And if you have that, then we remember that.
Wait, doesn't that mean that the target position is the count of truths in each row, or something like that? Like the number of numbers.
Yeah.
The number of numbers is larger than that's its target position. So the selector width just computes the sum of.
That sounds right.
Something like that.
Yeah. So we have that, and we take another built-in, which is indices, and we take this computed sequence, as you said, is the target position, and we say we ask if a given index is equal to the target position, and then we aggregate our input tokens over that, and this is how we get a sorted set.
By the way, I'm pretty sure in the first line we need a smaller instead of smaller than equals, because then we'll have then if we have an array with all equal numbers, then they would all have the same target position.
That's alright, because we are sorting into a set. So okay. Yeah. Yeah. So this is an example of program in this language. And do we also want to try to look at these attention maps? I really don't like looking at attention maps. Do you have an interpretation here? Yeah, maybe not. Well, yeah, let's just skip the attention map. Okay, so that was how the program looks like. And I think that from now on we can let me just briefly cover what the 2021 paper is about, and then we'll get to the 2023 paper. And yeah, I think this is the right section. So further reading, if you're interested in, is to see they discuss how exactly those primitives we saw relate to the architecture. But this is basically, as you said, that element-wise MLPs and select aggregate attention. And implications and insights is basically about how you can use this language to study restricted transformers. So there is this meme that transformers are quadratic in sequence length, yeah, and there was work about doing something so that they are not quadratic, so they are n log n or even O of n, and sparse attention, or some soft attention stuff and things. And if you think about these transformers in terms of RASP, then this can be insightful. Like some of our selection matrices will always be false. Some of our elements in the selection matrix will always be false. And like I think it's like generally much easier to think in terms of like how this might limit the expressive power from here, like than from just you just took the attention. Is it that does it make sense?
What do you mean by limit? So we know that, for example, in the comparison selection, most of the rows will have a lot of falses because there's the ordering of the numbers, for example. So
I mean that if you have a general, like if you have a standard transformer, then then the matrix you will get from the select operation will have like n bits. But if you have a restricted transformer, that some of those entries of the matrix just by architecture.
Because it's smart extension.
Yeah.
Okay.
So like you have fewer bits of information. You like some information gets lost, and like
Sure.
this limits the kinds of algorithms we can represent. And I'm saying that it's maybe easier to think like from this perspective than like from just the transformer architecture. Oh yeah, they even have some result here. In appendix B, we represent like a sorting algorithm. I assume like just standard sorting, like array to array. Input sequences are arbitrary length and alphabet size. And it is a computer science result that this is omega of n log n. And this entails that if you restrict the transformer to n log n or less, then you supposedly can't do like sorting in it. And this is like interesting.
If we can do sorting, that means that we can't go lower than n log n.
Yes.
But to be fair, n log n is for like sorting objects that we can compare. Whereas if we have a fixed alphabet, there are algorithms that do faster than n log n.
Yes. But like the general agenda here is that here we went like from some WUI like floats to like concrete computational problems which we can reason about in a standard way. And also like some stuff about other like architectures related to transformers, which I'm not going to cover. Like how special tokens influence the picture. Yeah, so like check the paper out if you're curious about that. And now the final boss, the 2023 paper. Let's see what we can get away with skipping. So, like what the previous paper did, it was called Thinking Like a Transformer, and it introduced a language. It introduced RASP. And what this paper does is it introduces a compiler for this language, which is called Tracr, and it introduces a bunch of interpretability experiments. And so I suppose that if we are to, like we have a section about how the compiler works. We have this is all stuff that we covered already. Let's see what we do want to cover today.
So that paper didn't have it, but this paper does the path from the program to the transformer architecture.
I think that the earlier paper, it kind of like had a simple translator, and this one is more interesting. Yeah, okay, so let's try to cover sections 3 in some detail and section 4 and section 5 in like quickly. So section 3, a transformer compiler. Let's see how this works. we embed RASP in Python, so like an embedded domain-specific language, which means that we can like use Python functions, which then get like I don't know, which then our translator takes and compiles into something else. And then we have an intermediate representation, which is called craft, which corresponds to like assembly. So like if in normal compilers you have like machine code, here we have transformer. If in normal compilers you have assembly, here we have craft, and in our programming language is RASP. Yeah, let's maybe try to understand that. So craft is a transformer implementation by vector spaces in labeled base dimensional operations, which basically means that I think that this makes our transformer retargetable. So if we can act on different vector spaces, this might give us. I wonder if this gives us independence on implementation details, like if we compile down to like float 32 or float 16.
Presumably.
Yeah, presumably. All right. So
I'm not actually sure how optimization would act on such architectures, because we built down in number of bits that we have, we lose precision, and hence we might lose on the level of input, the kind of logic that we have here.
Yeah, I mean, a nice question. I don't have an answer. So let's try to go through the flow of the compilation and then see like if we can improve it anyhow. First, we do kind of we kind of trace the data flow. So we have our program is written as as something like that, and like we have from here we can maybe we actually have we have a simple program here. Let's go with this. So like for every token we check if it's equal to x, and then we again do like our less than or equal thing and aggregate by that. And because aggregate does averaging, what this is going to do is compute the fraction of x's before this token at each position. Like we have this data flow diagram. If we instantiate it with like this constants, then this is how it's going to compute. And if we have a data flow diagram, then like for each kind of operation, exactly as you said, we translate it either to an MLP or to attention. So like here we have like built-in, like I don't know, in terms of the programming language, it's built-ins. In terms of like I don't know, like these are like our inputs, and this is like our representation of positional encoding, and we translate the equals to x to an MLP. This is a standard library thing, which is also represented as this sort of graph, which we just inline when we compile. And this aggregate operation is attention. And this was like we like step 1, we construct this data flow graph. Step 2, we technical detail. We need to figure out the domain at each step, just to figure out like how large this block will be. Because if the block only works with 0 and 1s, it needs to be this wide. If it works with this given alphabet, it needs to be wider. Then each block we translate to a transformer block, and then we do allocation. That is, we from this like abstract graph, we build a layered model. So like each block needs a place in like it's a layer to belong to. Yeah, I know, like some inference of like depth inference, layered inference, residual stream inference to fit all that. So that was how the compilation works, and something I'm only going to go through very briefly here. Again, like the source is somewhat readable. So this compilation gives us a kind of a particular kind of bound on what we get, like, because this compilation is like somewhat naive, and what we expect to get is we expect to get like sparse and orthogonal features. And what we normally get in deep learning models is like some weird shit, also known as the superposition agenda nowadays. And so what we can do to like make our result more like real world grounded is when we get like this sparse and orthogonal transformer from our compilation. What do we do? We freeze our weights, and we want to compress the residual stream, and so we train W, which is a matrix which so like whenever we touch the residual stream, we multiply by W, and we learn W. So we learn some compression matrix. And we learn it like with standard optimization. And this basically makes our models more interesting, and it's also interesting to see what is learned in the compression. And we also do a bunch of evaluations to see if the compressed models still do the same thing. I'm not sure how to summarize this well. Like I'd say, like when we ask this question, we get some answers. So, like, do the compressed models still plan the same computation? It depends. And this is basically this paper. Any comments here?
I guess they didn't aim for like some finalized research goal. They wanted to make a step towards something.
Oh, I mean, what I kind of skipped is I think they are supposed to have some evaluations somewhere. Let's see, will it work? Well, like maybe not in this paper, but I'm sure they have like a website. Like this work group has some resources where they encode different algorithms in RASP and Tracr, and then say that like a transformer, like a variation of transformer this and that, can encode an algorithm something or other.
And this means something about commercial abilities, that with enough layers we can get these super abilities. It makes sense that these large models do this.
Well,
I said like there's some implications.
Yeah, I'd say the like I think the way they think about implications is in terms of like so like we saw this result that you cannot restrict a transformer beyond a particular point if you want to have some nice things. And like I think their agenda is about finding out like on one like thing one, what like how much expressive power do you actually want, and so like what are our limits in terms of architecture. So like which architectures probably won't work, like just in terms of like standard computability. Then there is I lost the thought. Then there is stuff like if so this also works to so like what I just said was about like architecture in general, so like sparse attention, but we can also think of it in terms of like to solve this particular problem we need a transformer this big, because this thing gives us like a bound on width and depth and like number of heads and this stuff. And like what this tells us is that like some problems are soluble, and if a given problem looks like a soluble problem and isn't solved, then like maybe like it actually is. That makes sense? Yeah. And this is one particular agenda of understanding what the models work and like how what are their limits, and like just to reiterate, so the way this agenda works is that we say that a transformer can simulate a particular machine, like a particular like stack automata, push-down automata, something. We can check if it indeed does that by like taking old school formal languages, which it can either recognize or not, and like this is the agenda to find out the like computational limits in time and space of transformers. Also, like I do understand that this paper, I'm not actually sure, like a complexity class. Yeah, like this paper doesn't mention complexity classes like at all. I know that, but I think that this is what they're kind of aiming towards. They're just not there yet. And this is like a very different way to think about deep learning. It is very similar to like thinking about like sorting algorithms or like like tree traversal algorithms. And it can be nice in that it gives us tight bounds. So like for any input, we get an answer in this span of time, like in this space. Or like what is more interesting for transformers is that. So a transformer is basically an algorithm which we found in the space of our algorithms, right? So what we care about is not that a transformer like solves this in given time, is that we can find this transformer in a given time. And so like I think this agenda like at its best is about like we have a space of deep learning architectures, and if we know that we want to like that our problem requires sorting and look ahead, because like I don't know, because it is about because it is like about so we can if we think about language models, then we can ground some questions in terms of linguistics, like if you want to do named object recognition, then you like have to do this and this. I'm sure linguists know what you have to do, I don't. And like when you are like an ML practitioner, you say like, okay, I need to recognize named entities. I need to like find a new model which does that. And in this like space of all possible architectures, I'm only going to do transformers because they're trendy. But like I also know that I need at least this number of heads, at least like this number of MLPs, or for this alphabet size, it just like won't work. And this is like very distinct from how deep learning is done these days. I think like useful. It is like one of the ways to make this into more of a science than art as now.
Right now it's alchemy.
Yeah. So like here are some real computer scientists trying to make it into real computer science.
But the idea of compiled language that can compile your network architecture solves, because this implies that we can do the cross operation. We can take an architecture or a trained model, decompile it into a massive code, but even though we cannot interpret the whole thing, most probably, we can basically look for certain things and try to estimate if this computer does this kind of thing that we look for, which is maybe possible if you look at it.
Well, like one of those papers we went through cites prior work which does this with RNNs. Like they decompile an RNN into an automata, into DFA. Yeah.
That's cool.
So, any other comments? All right, then I think we're done this day. Yeah, we looked at modeling the statistical chances of love, found some future directions for that, and we also went through a pretty dense bunch of papers on like this one agenda in making deep learning science, which we just did. Yeah, thank you.
And about the moon, I often